Mathematics, St. Thomas College, to welcome the resource person.
Am I audible?
Yes, sir.
Okay. Good evening to all. Now, we are moving to the final session of our instructional workshop on advanced cryptography. I would like to introduce our resource person, Dr. Saju M.I. Dr. Saju M.I. is the head of Department of Mathematics and Research Guide at St. Thomas College, Thrissur. The thrust area of his research are algebra and cryptography. Dr. Saju M.I. earned his PhD from University of Calicut. He has around 10 publications about public key crypto systems. On behalf of all the participants gathered here, I invite Dr. Saju M.I. to handle this session.
Okay, thank you, Anthony John. This is the last section of our program, IWAC-2023. In the previous sections, we discussed the various areas of advanced cryptography. So, in this modern world, the knowledge about cryptography is significant. Everybody asks, even after completing MSc Mathematics, our students ask, what's the role of algebra, number theory, linear algebra? What's the use of a plus b whole square? The answer is cryptography. Even our computer students said that mathematics is a difficult subject. But actually, mathematics is the language of computer science. Here we see that all difficulties and confusions that we face with the mathematics are merits of cryptography. Mathematics is the fundamental to cryptography. Dear students, it is a workshop in online. It is a difficult task, I know. So don't sit as a mere listener, ask doubts. Okay. In this section, I shall give you some mathematics behind cryptography. Not in advanced level, only some mathematics behind cryptography. Okay. Shall I share my PPT? Is it visible?
Yes, sir. The PPT is visible.
Okay, thank you, thank you. So my topic, the role of primitive polynomials in crypto. We know that every system, every crypto system, we heard about the digital signature, encryption, decryption, etc. We need a field, okay? We need a finite field. So first we know about the knowledge of Galois field. The French mathematician Galois. He died at the age of 21. At the age of 21. Galois theory provides a connection between field theory and group theory. So a finite field or Galois field is a field that contains a finite number of elements. So for the construction of a finite field, we need a prime number. For every prime p and every positive integer k, there are fields of order e raised to k. That is the result from field theory. For each prime p and a positive integer k, there exists a field with the e raised to k elements. At the same time, every field with the p raised to k elements isomorphic to a Galois field of order p raised to k is denoted by GF p raised to k. Okay. So how can we construct Galois field using irreducible polynomial? Okay. First we take a polynomial f of x equal to x cube plus x plus 1 over f2. Over f2 is set to, okay, it is irreducible because over f2 we know that in f2 there are two elements, 0 or 1. F of 0, here f of 0 is 1, f of 1 is also 1. So it is irreducible. It is a irreducible polynomial. Then we have a quotient ring f2 of x by ideal f of x. Its order is 2 raised to 3. And it is isomorphic to GF 2 raised to 3. So, first we need a Galois field for the construction of a CRYPTO system. For this, we need a prime number and a positive integer n. When we take a prime number as large as possible, we get a large finite Galois field, p raised to n order. Next, we discuss about primitive elements. In field theory, a primitive element of a finite field or Galois field GFQ is a generator of the multiplied group of the field. It generates all the non-zero elements of the field GFQ. In other words, suppose alpha be the primitive element, then it is a q minus 1th root of unity. Q minus 1th root of unity. Alpha raised to q minus 1 is 1. This means that each non-zero element of GFQ can be written as some power of alpha. Okay, so every non-zero element of GFQ, Galois field GFQ, can be written as some power of alpha because alpha is the primitive element. Alpha generates all non-zero elements of GFQ. So any element of GFQ is some power of alpha. For example, consider the multiplied group of the field is at 13. Here the prime number is 13. Compute 2 raised to I. Here I varies from 1 to 12. We know that 2 raised to 1, that is congruent to 2 mod 13, 2 square, congruent to 4 mod 13, 2 cube, etc. 2 raised to 7 is 11 mod 13. Here we see that there is a one-to-one map between 2 raised to I and Z13 star. That means Z13 star, that is the non-zero elements of Z13. 2 generates all the non-zero elements of Z13 star. So 2 is a primitive element of Z13 star. The other primitive elements, first we have to calculate and find out a primitive element in GFQ. After that, we can compute other primitive elements also. There is a method for that. There is a result for that. The other primitive elements are 2 raised to j, where j belongs to units of 12. Units of 12 means the unit is relatively prime to 12. Here we work in GCD. GCD of J12 is 1. So we know that the units of the elements in U12 are 1, 5, 7, 11. So there are 4 units. Invertible elements. Units means invertible elements. Multiplicative ways exist. So the primitive elements are 2 raised to 1, 2 raised to 5, 2 raised to 7, 2 raised to 11 in mode 13. We have 2, 6, 11, 7 more. So the primitive elements of Z13 star, primitive elements are 2, 6, 11, 7. So this is the idea. So when we have a primitive element, then we can compute other primitive elements of the multiplicative group. Here 2 is a primitive element. Then other primitive elements are 2 raised to j, where j belongs to units of 12. So first we have to compute the units of 12, find out the units of 12. Then 2 raised to j are the primitive elements of Z13 star. Here there are 4 primitive elements, 2, 6, 11, and 7. So generally, number of primitive elements in ZP star is Euler-Torsion function phi of p is prime. So we know that phi of p is p minus 1. So that is phi of p minus 1. And if A is a primitive element, then A raised to j belongs to units of p minus 1. The last example, we see that 12, p of 12. Okay, we take, in that case, we take the pi number p is 13. So here A raised to j, here A is a primitive element. So A raised to j belongs to units of p minus 1. Units of p minus means the elements in relatively prime to p minus 1. So this is the idea for primitive element. One more example, we can take one more example. Here we take a pi number is 29. So Z29 star. These are the elements. Here phi of 29 minus 1 is 28. Phi of 28, that is 12. So here there are 12 primitive elements. So we can easily compute this. This is the mathematical meaning. So primitive element is an important idea in the construction of crypto system. So we have first we have to know the idea of how to generate primitive element. of a Galois field. How to find a primitive element in the Galois fields. Here we see that 2 is a primitive element. Then 2 generates 2 more 29s, 2 square more 29s, 4, etc. Last we see that 2 raised to 28 is 1. So 2 generates all the elements of, all the non-zero elements of Z29 star or F29 star. So to find the other primitive elements, first compute the units of 28. Here, units of 28, 1, 3, 5, 9, 11, 13, etc. So the corresponding primitive elements are 2 raised to j. Okay, 2 raised to j. J is 1, 3, 5, 9, 11, etc. So we have the primitive elements 2, 8, 3, 19, etc. This is another way to, we have to know if element is in a field, the element is primitive or not. It's a question. Consider is a 17 star. Here, phi of 17 minus 1 is 5 or 16 equal to 8. So there are 8 primitive elements. You have to check 2 is a primitive element or not. Primitive element means its order is, if A is a primitive element, then its order is in ZQ is Q minus 1. Q minus 1 to root of unity. That is the meaning. So here, when we check 2 is a primitive or not, that is, we have to check 2 has order 16 or not. It works in 17, so Q minus 1 is 16. So we have to check 2 has order 16 or not. So we have to check whether 2 meets its order less than 16. We already know that by Fermat theorem, 7 is a prime number. So 2 raised to 16 congruent to 1 more to 17. That is always true. Because 2 is relatively prime to 17 by Fermat theorem. So 2 raised to 16 is 1. So 2 raised to 16 is 1. So we have to check the order of 2 is 16. Here we know that the divisors of 16 are 2, 4, 8, 16. Okay. So what is 2 square? 2 square is 4. Mod is 17. 2 raised to 4 is 16. 2 raised to 8. 2 raised to 8 is 256, but that is congruent to 1 mod 17. That means order of 2 is 8, not 16. So 2 is not a primitive element. Okay, if 2 is a primitive element, then its order should be 16. But here, order of 2 is 8. So 2 is not a primitive element. Similarly, we have to check 3 has order 16, 3 primitive element or not. 3 is a primitive element or not. 3 is relatively prime to 16 by Fermat theorem. We have 3 raised to 16 congruent to 1 mod 17. So we want to check whether 3 meets its order less than 16. Less than 16. So the devices of 16, they are 2, 4, 8, 16. Okay. So compute 3 square. 3 square is 9, mod 17. 3 raised to 4, that is 13, mod 17. 3 raised to 8, that is 16, mod 17. So we can't meet 1, okay? So the only possibility for order 3 is 16. So order of 3 is 16. Okay, then 3 is a primitive element. So in Z17, we get a primitive element, that is 3. Then we can compute other primitive elements of Z17. That is, first we have to compute the units of 16. Here the number, here the prime is 17. So 17 minus 1 is 16. So units of 16. That means the number is relatively prime to 16. They are 1, 3, 5, 7, 9, 11, 13, 15. Okay. There are 8 units in Z17. So the primitive elements are 3 raised to 1, 3 cube, 3 raised to 5, 3 raised to 7, 3 raised to 9, 3 raised to 11, 3 raised to 13, 3 raised to 15, mod 17. So we have 8 primitive elements. So that is the idea of primitive element. So the primitive element, the element who can generate all elements of ZB star. Okay. So these are the examples for primitive elements. First, we come to the point, primitive polynomial. What is primitive polynomial? Primitive polynomial is an irreducible polynomial. Its roots generates all non-zero elements of Galois field. So it is an irreducible polynomial. First thing, it is an irreducible polynomial. Then its roots generates all non-zero elements of Galois field. So primitive element is the root of the root of primitive polynomials are primitive elements because they generates all non-zero elements of Galois field. There is a result. The number of primitive polynomials over Fp will be phi of p raised to n minus 1 by n. So we have a finite for a Galois field. We get for a prime p and a number n. We get phi of p raised to n minus 1 by n primitive polynomials. Okay. For example,
Hello, excuse me, sir. Hello.
consider f2 of x. There are,
Sir,
okay,
so there is a participant. Raise your hand.
okay,
Excuse me, sir.
yes.
Sir,
Tell me.
in the previous slide, what is the n?
n is a positive integer. Yes?
So, means it can be any positive integer
Yeah.
or a degree of a polynomial like that.
Ah. Degree of the polynomial is n. Hello.
Hello, sir. Hello.
N is the degree of the polynomial.
Okay, sir. Okay.
Degree here a positive integer.
Okay, sir.
So any positive integer n, any odd, any prime p. Okay, we have a Galois field with the p raised to n elements. So in a Galois field with the p raised to elements, we can find out phi of p raised to n minus 1 by n primitive polynomials. Okay. Primitive polynomial, the root of primitive polynomial, that is a primitive element. That means that generates all non-zero elements of the Galois field. Non-zero elements is a multiplicative group, cyclic group. So it has a generator. Okay. So here the primitive element acts as a generator of FP, that Galois field. So when we take a large prime number and a large positive integer n, then we have a large collection of primitive polynomials. Okay. Because every construction, every system, we need a field. That is the basic idea. Without a finite field, we cannot develop or construct a system. So we need a prime number. We need a positive integer n. So every field with the p raised to n, that is there's another idea. Every field with the p raised to n elements, they are isomorphic. That means there is only one field with the p raised to n elements up to isomorphism. Okay. So here an example. Degree 3. How many primitive elements are there? Phi of 2 raised to 3 minus 1 by 3. That is phi of 7 by 3. That is 6 by 3 equal to 2. So there are 2 primitive polynomials. Excuse me. 1 second. Okay, is it visible? Okay, is it visible?
Yes, sir.
Audible?
Yes, sir. Yes, sir.
Okay. So time 8 o'clock. It's a siren. Okay, anyway. So there are 2 primitive polynomials of degree 3. They are, there is a correction. First one is x cube plus x plus 1. Second one is x cube plus x square plus 1. Not x. This is a reducible polynomial. Okay. When I put x equal to 1, x cube plus x square plus x 1 is reducible. So it is not a primitive polynomial. Actually, the primitive here, there is a typing mistake. This polynomial is x cube plus x square plus 1. Okay, so there are 2 primitive polynomials of degree 3. In the case of degree 5, phi of 2 raised to 5 minus 1 by 5, phi of 31 by 5 equal to 6. So there are 6 primitive polynomials of degree 5. Okay, these are so when we so the primitive polynomials, we need primitive polynomials for the concession of all the concessions. In the case of concessions, we want primitive polynomials. And so I discussed this better. Okay. Next, what are the elements in GF2 raised to 3? Like another example, we know that x cube plus x square plus 1 is an irreducible, and it is a primitive polynomial. Okay, because if x is a root of f of x, primitive polynomial means its roots generates all the non-zero elements of Galois field 2 raised to 3. Okay, here degree is 3 over f2, basic field f2, 0, 1. Okay, if x be a root of f of x, if x is a root of f of x, then generate x. Then if x is a root, then x cube plus x square plus 1 is 0. Yes, then x cube is minus x square minus 1. But over f2, minus 1 is plus 1. So x cube is x square plus 1. Okay. So when we generate x, first element is x, then x into x square. Then next element is x cube. But x cube is x square plus 1. Then what is x raised to 4? That is x into x cube. So x into x square plus 1. That is x cube plus 1. But x cube is x square plus 1. So x raised to 4 is x square plus x plus 1. Similarly, what is x raised to 5? That is x into x raised to 4. Multiply this by x. So we have x cube plus x square plus x. But x cube is x square plus 1. Okay. So we get x plus 1. 2 times x square is 0 because here the field is f2. Characteristics 2. So 1 plus 1 is 0 here. So 2. Here 2 is 0. Okay. So here x plus 1. Then what is x raised to 6? X into x raised to 5. This is x raised to 5. Into x. So x square plus x. Okay. Then again multiply by x. That is x raised to 7. What is x raised to 7? X cube plus x square. X cube plus x square. X cube is x square plus 1. So x square plus x square plus 1. X square plus x square is 0. So we have 1. So x raised to 7 is 1. So we get all the elements of GF 2 raised to 3. All the non-zero elements of GF 2 raised to 3. There are 7 non-zero elements. X square plus 1. So this is, we see that these are the polynomials of degree less than 3. The collection of polynomials of degree less than 3. Yes. Collection of polynomials of degree less than 3. So what are the elements of GF 2 raised to 3? there are 8 elements. Okay, in the Galois field 2 raised to 3 there are 8 elements. Common people said that 0, 1, 2, 3, 4, 5, 6, 7. That is computer science students. This is the second row for computer science students. Third row for mathematics students. Because here we note that x raised to 5 is x square plus 1. Check the coefficients of this polynomial. 1x square, 0x plus 1. 1, 0, 1. 1, 0, 1. Coefficient of x is 0. Here, this is a polynomial of degree 2. So its coefficients are 1, 0, 1. That's the bits 1, 0, 1. So 1, 0, 1. That is the binary system 1, 0, 1. That represents the polynomial x square plus 1. Similarly, what is 1, 1, 0? 1, 1, 0, 1x square plus 1x plus 0 constant. That is x square plus x. So it's a polynomial. Is the third row. So these are in form of binary bits, the form of polynomials. Or 0, 1, 2, 3, 4, 5, 6, 7. This is 7. 1, 1, 1. What is 1, 1, 1? Binary to decimal. 1, 1, 1. 1 into 2 raised to 0 plus 1 into 2 raised to 1 plus 1 into 2 square. That is 4 plus 2 plus 1. That is 7. Okay. So these are elements of GF 2 raised to 3. Here we take the prime P is 2. We take any prime here. In place of 2, take any prime. Suppose the prime is 3. So we have the coefficients are either 0 or 1 or 2. Okay. Commonly we use the prime p equal to 2. So I write this way. Okay. Any prime we can use for this. So first we see that what is primitive polynomial? Primitive polynomial is an irreducible polynomial. But irreducible polynomial need not be primitive. All irreducible polynomials need not be primitive. Irreducible does not imply primitive. For example, here we have a polynomial f of x equal to x raised to 4 plus x cube plus x square plus x plus 1 over f2. Okay. X is a root. It is irreducible because when put x equal to 0, here over f2, so here only 2 elements, either 0 or 1. So over f2, it is irreducible. When x is 0, here 1. When x is 1, 1 plus 1 plus 1 plus. So f of 1 is 1. Here addition modulo 2. Characteristic is 2. So 1 plus 1 is 0. Okay. So f of 0 is 1, f of 1 is 1. F of 0 is 1, f of 1 is 1. So this polynomial is irreducible over f2. Okay. Then what about the extension that we have to find the Galois field, that is the extension field of f2, GF 2 raised to 4. Here the Galois field is GF 2 raised to 4. 2 raised to 4. 16 elements. Okay. When we generate, suppose x be a root, when we generate x, first element is x, then x into x square, x cube. Then what is x raised to 4? From this, x is a root, so x raised to 4 is x x cube plus x square plus x plus 1. So x raised to 4 is x cube plus x square plus x 1. Then what about x raised to 5? X raised to 5, x into x raised to 4. Please check. X into x raised to 4. So x raised to 4 plus x cube plus x square plus x. But x raised to 4 is x cube plus x square plus x plus 1. So 2 times x cube, 2 times x square, 2 times x all also, then we have 1. So x raised to 5 is 1. Okay. So when we generate the root of f of x, we get only 5 elements of the Galois field. X, x square, x cube, and this one and one. So the root of f of x not generate all non-zero elements of the Galois field GF 2 raised to 4. So it is not a primitive polynomial. Okay, so all say primitive polynomial that is irreducible, but convex need not be true. Irreducible polynomial need not be primitive. Okay, that is an important point. If x is a root of primitive polynomial, if we have a root primitive element in f of x, then we can compute other roots of the polynomial. That means if f of x be a primitive polynomial of degree n over fp, that means x is a root of f of x, then there is a result, very important result. That is the other roots of f of x, the other roots of primitive polynomial are x raised to p, x raised to p square, x raised to p raised to 3, etc., x raised to p raised to n minus 1, n minus 1 are other roots. For example, f of x equal to x raised to 5 plus x cube plus 1. It is a primitive polynomial. X be its root. X is a root. Okay. Then here prime is 2. So x square, x raised to 2 square, x raised to 2 cube, x raised to 2 raised to 4, x square, x raised to 4, x raised to 8, x raised to 16. These are the 5 roots. Here f of x is a 5th degree polynomial. So it has 5 roots. They are x square, x raised to 4, x raised to 8, x raised to 16. So these are the roots of f of x. These are the elements of f, our Galois field 2 raised to 5, GF 2 raised to 5. There are 2 raised to 5 elements in GF 2 raised to 5, okay? In which x square, x raised to 4, x raised to 8, x raised to 16 are roots of f of x. So when we have a root for a polynomial, then we can compute other roots of the polynomial, primitive polynomial. This is the idea. X raised to p is a very important result in field theory. X raised to p, x raised to p square, x raised to p raised to 3, etc., x raised to p raised to n minus 1 are other roots. Okay, now we come to another. We already heard about discrete logarithm problem. We know that for the construction of any crypto system, for the security of crypto system, we have to add the main raw material. That is the idea for the construction or development of system. We add a classical or mathematical problem into it. So DLP is one of the problems. It's a very tough problem, difficulty to solve. So DLP is a So what is DLP? First, the definition of DLP. Discrete logarithm problem. It's the problem of finding solutions x to the equation g raised to x equal to h. Here g, we already know that when in a cyclic group, an element generates all the elements. Okay. So g raised to x is h. That is easy. G raised to x is h. Okay. Then logarithm of h to the base g is x. That's the exponent. Exponent x. Exponent x is the logarithm of h to the base g. That is the definition of discrete logarithm. So discrete logarithm okay. That is, we know g and h. Then we have to find compute x, g raised to x, but we have to come. But so we have to find the exponent x. That is the logarithm of h to the base g. That is the discrete logarithm of g to the base g. This is a simple example. Suppose 3 raised to x congruent to 2 mod 7. That is z7 star. So when x equal to 1, that is 3 not congruent to 2 mod 7. 3 square. So answer is 2. Now, another example. Consider the field Z13. Our question is, find the discrete logarithm of 8 to the base 5. Discrete logarithm of 8 to the base 5. So, calculate 5 raised to 8. Generate 5. Here the base is 5. Okay. So 5 raised to 1, 5 square, 5 raised to 3, 5 raised to 4, etc. So from this table, we see that 5 raised to 3 is 8. 5 raised to 7 is also 8. Again, 5 raised to 11 is also 8. So that is the of 8 to the base 5. Logarithm of 8 to the base 5 is 3 or 7 or 11. So answer is not unique. So that is the discrete logarithm. It's a problem. We know the 5 we have to compute the exponent of 5. Okay. 5 raised to 3 congruent to 8 mod 5. 5 raised to 7 also 8. 5 raised to 11 also 8. So how can we compute the logarithm of 8 to the base 5? The answer is not unique. That is known as discrete logarithm problem. Because here the reason is from the fourth row, 5 raised to 4 is 1. 5 raised to 4 is 1. That means order of 5 is 4. Five raised to 7 into 5 raised to 4, 11, that's also 8. So order of 5 is 4. 4 not equal to order of Z13 star. So the discrete logarithm of 8 to the base 5 is not unique. In this table, we have 3 answers, 3, 7, and 11. Not unique. So that is the discrete logarithm problem. is another example. Find the discrete logarithm of 7 to the base 2. 7 to etc. 2 raised to 12 is at 13. So up to 2 raised to 2. Here 2 raised to 12 is 1. So order of 2 is 12. Okay. Order of 2 is 12. That means 2. So there is a 1 between 2 raised to I and Z 13 star from this table. Okay. Modulo 13. Okay. 2 raised to 12 is 1. 2 raised to 12 is 1. When 7 plus 12, 2 raised to 7 is 11. What about 2 raised to 7 plus 12? That is 2 raised to 19. That is also 11. So we can see that there is a one-to-one map, but still there is a problem because we choose the exponent as our secret key. Okay, then it's another example in terms of polynomial. Okay, we consider in a Galois field, we take a primitive polynomial f of x equal to x cube plus x square plus 1, x cube plus x square plus 1 over f2, and I consider x be a 0. Then what is x into x square? What is x cube? X cube is x square plus 1. X raised to 4 is x into x square plus 1. That is x cube plus 1, x cube plus x. X cube is x square plus 1. So we have x square plus x plus 1. So what is the discrete logarithm of x square plus 1 to the base x? 3. Discrete logarithm of x square plus x plus 1 to the base x is 4. Okay. So when we take a large prime, too difficult. So in these systems, for the security, we apply the concept of DLP. DLP is the security of these systems: L-GAML signature scheme, L-GAML encryption, Diffie-Hellman key agreement system, digital signature algorithm, elliptic cryptography. So here the DLP, solving a DLP, not easy. So difficulty of DLP is the security of many crypto systems. I'll give you a simple example. Okay. Consider Z29 star. Okay. A equal to 8. That means we take the primitive element 8. 8 is the primitive element. 8 generates all the elements of Z29 star. 8 is a primitive element. And take a key. Here key k equal to 9. So here k equal to 9. 9 is the secret number. K equal to 9. Okay. Our plain test is maths. Using the primitive elements 8, key 9. Okay. First, we write the numerical equivalence of the alphabets. Is at 29 star. So 1 to 28 elements are here. Each alphabet A maps to 1, B maps to 2, etc. Z maps 26, space maps 27, question mark 28. These are the alphabets and the corresponding numerical equivalents. Okay. Then what about the plain text max? The corresponding numerical equivalents MATHS. M maps 13. Okay. A 1 max MAT 20. Okay. H 8 S 19. So max. The numerical equivalence of the plain text max is 13, 1, 28, 90. So 1-to-1 mapping. Then here we take the primitive element is 8. So this is the table. 8 generates 8, 8 square, 8 cube, modulo. Okay, modulo 29. So 8 square is 6. Here works in modulo 29. So these are the elements. 8 square is 6. Okay. So our plain text is max. Check the first letter M. M maps to 13. M maps to 13. 13. Here check 13. 13 is 8 raised to 6. Mod 29. 8 raised to 6. So M, the first letter for the plain text max, 8 raised to 6. M is 13. 13 is 8 raised to 6. Similarly, other alphabets, other numbers. Okay. So this is the plain text max, MATHS. That maps into 8 raised to 6, 8 raised to 28, 8 raised to 8, 8 raised to 1, 8 raised to 3 from the previous table. Okay. So this is max. This is max. Then we apply an encryption rule. We can use any rule for encrypt the test. Our test is 8 raised to 6, 8 raised to 28, 8 raised to 8, 8 raised to 1. 8. This is our plain test. Then we apply an encryption rule. Okay. Here I take an encryption rule as M A raised to K. M is the test, plain text. Each letter, each character multiplied by A raised to K. We choose A as 8. Okay. 8 raised to K choose as 9. Okay. In the previous table, A is 8, K is 9. K is 9. Okay. So our cipher test, this is the process. M A raised to K. 8 raised to 6 into 8 raised to 9. We get 8 raised to 15. 8 raised to 28 into 8 raised to 9. 8 raised to 28 is 1. So 8 raised to 9. This way. So this is the cipher test. This is our plain test to max that maps into cipher test. This is our cipher test. This is the calculation. 8 raised to 6 into 8 raised to 9. Okay. Multiply each character, max. Max correspond, we see that this is max. Multiply by 8 raised to 9. 8 raised to 9. 9 is our key. Okay. 8 raised to 9. Multiply by 8 raised to 9. So we have this. This is our cipher test. This is the computation in modulo 29 now. So this is our cipher test. Then what is 8 raised to 15? 8 raised to 15. From the, this is 8 raised to 15. Okay. So we have the corresponding alphabets U, O, J, D, X. 8 raised to 15 is 21. 21 is U. Okay, 8 raised to 9. 8 raised to 9, that is 15. Oh, this way. Anyway, so we have, this is our cipher test. So max, the plain test maps into U, O, J, D, X. This is the cipher test. This is the calculation. Yes, we have 21, 20, 10, etc. Similar way, we can, that is the encryption process, the reverse process, and the reverse process of encryption, that is, we know that is decryption. In the reverse process, this is our cipher test that maps into max. In the case of decryption, our key is 9. Encryption key is 9. So what about a decryption key? Minus k. That is 19. Okay. 9. That's additive inverse of k. Additive inverse of 9 minus k. That is 19. So this is our cipher test. Corresponding numerical equivalency area. Then this is our cipher test multiplied by 8 raised to 19. Each number multiplied by 8 raised to 19. Then we have 8 to 6, 8 to 28 this way. That is 13, 1, 28, 19. That is max. So that is the decryption process. Here, the key K is 9. That is the exponent of 8. The secret security of the system is DLP. Okay, so it's a simple idea. The role of mathematics in the encryption, we can apply any type of encryption rules. This encryption rule is defined by us. It's a simple example. We can apply any type of encryption rule here, multiply any rule, then we have the test. Okay. Now we can define the DLP in the extension fields. Okay, definition of discrete logarithm problem on extension fields. Consider a polynomial x raised to 5 plus 1. It is not an irreducible polynomial. It is reducible. It's a polynomial, simply a polynomial over f2. X is a 0. So find the discrete logarithm of x raised to 4. Then we compute x congruent to x mod x raised to 5 plus 1. These are the divide x raised to 5 plus 1. Divide x by, so this x square congruent to x square. This one, x cube is congruent to x raised to 4 is this one. What about x raised to 5? That is congruent to 1 mod. This way. So x raised to 5 is 1. So order of the logarithm of x raised to 4 to the base x is 4. X raised to 5 is 1. So x raised to 4 into x raised to 5, that is again x raised to 4. So x raised to 9 is x raised to 4. So discrete logarithm of x raised to 4 over the base x will be 4 plus multiple of 5. So the values of the discrete the value of discrete logarithm of x raised to 4 to the base x is 4, 9, 14, etc. There are infinitely many solutions. There is no uniqueness. So it is a problem. Because order of x raised to, here x raised to 5 is 1. That is the problem. So here x raised to 4 into x raised to 5 is again x raised to 4. So adding plus 5. Okay, 4, 9, 14, etc. So discrete logarithm of x raised to 4 to the base x is 4, 9, 14, etc. There are infinitely many solutions. So that is the discrete logarithm problem. This is the problem. Okay. Consider ring of polynomials over the field F2, f of x equal to this one. Then how can we find the discrete logarithm of x raised to 4 plus 1 to the base x? We have to find the exponent of x. X raised to something equal to x raised to 4 plus 1. Logarithm of x raised to 4 plus 1 to the base x. We have to find the exponent of x. Okay. So generate x square, x cube, etc. X raised to 4, x raised to 5. Here x raised to 5 is x cube plus 1. Then x into x raised to 5, x raised to 6, 7, 8, this way. Then we get when x raised to 25, x raised to 25 is x raised to 4 plus 1. That means discrete logarithm of x raised to 4 plus 1 to the base x is 25. Okay. X raised to 31 is 1. So in this table, logarithm of x raised to 4 plus 1 to the base x is 25. Because x raised to 25 is x raised to 4 plus 1. So these are the we can also discuss a simple example for this. Here the elements are polynomials. This is the primitive polynomial. Key is a number 20 and x raised to 20 is a polynomial. All elements are, because here he works in a Galois field, extension field. Here the plain text is max. Then each letter corresponds to a polynomials. M maps to this polynomial, M-A-T-H-S. Mathematically. Okay, these are polynomials. Each letter, here the numerical equivalence. Here we represent the numerical equivalence as polynomials. So polynomials, M-A-T-H-S. Here also we apply the same idea, m into x raised to k. This way we get the cipher test. Here the elements are m plain test. The elements are polynomials. X raised to k is a polynomial. Then multiply this mod f of x. We get this polynomial. So this is our cipher test. Okay. So each letter A is a polynomial x, B, x square, x cube. So each alphabet maps into a polynomial, okay, of degree less than 5. So this is the calculation, plain test into x raised to k. X raised to k is the polynomial. Each letter in the plain test, that is a polynomial, then multiply by another polynomial. Yes, we have the cipher test. So cipher test is a sequence of polynomials. This is the reverse process, decryption process. Okay, here we use the decryption key minus k. That is the additive inverse of k. maps to max. So here all the elements are polynomials. So for this, we select a primitive polynomial, then we have a Galois field, then each lecture in the plain text maps into a non-zero element of the Galois field. Then using an encryption rule, using a key for getting key, we have the knowledge about the discrete logarithm problem. The difficulty of discrete logarithm problem is the security of the system. So we use a large pi number, large Gauss integer. This problem is the complexity of the system is increases. So that is the idea. These are the decryption process. Multiply the polynomials by c x raised to minus k this way. Here f of x is a primitive polynomial. Then we have the plain text max. Okay. Then that's all. I think this is the best time to stop. So anyway, my idea is in every step in the development of crypto system, we have the idea of results from Galois theory, from algebra, number theory. They are very important, linear algebra. Okay, thank you very much. Ask any doubt. If you have any doubts, please ask me. Any doubts? I hope this section will help you some ideas in your future study. Okay. Audience, any doubts? Okay. Vijay ma'am?
Yes, sir.
We have to stop this time?
Okay, sir. If the audience have no doubts, then we may go to the concluding session.
Okay.
I now request Mr. Anthony John to conclude the session.
Good evening to all. I am very happy to express vote of thanks to our resource person, Dr. Saju M. Dr. Saju M. explained the Galois field, primitive elements, primitive polynomial, DLP, etc. in detail and their role in cryptography. I am very sure that all the participants will be benefited by this. Sir, we express our sincere thanks for your excellent presentations. Thank you, sir. Thank you so much.
Thank you.
Thank you, sir. Participants, please note, the link to submit the feedback form of the session is shared in this Meet chat. Kindly submit it without fail. Thank you.